Okay, good day, everyone. So my name is Nemeka, and I'll be your host for today. Um, so today we'll be talking mostly about the attention mechanism, right? Okay. Can you hear me? Choma, can you hear me? You're the one that complained about sound. Can you hear me? Hello, can you guys hear me?
Yes, yes.
All right. Okay, so let's wait for a couple of minutes before we start, or should we? Okay. So let me share my screen, share my slide. Okay, please tell me you can see my screen. Can you see my screen? Okay, hopefully you can see my screen.
Yes.
All right, so good day from wherever, good evening, good afternoon. And today we'll be talking mostly about the attention mechanism, and we'll be exploring the whole idea behind the attention and or what it means and how it flows. So let me just see. Okay, so we'll be talking about the transformer attention mechanism and its calculation, its the embedding and position layers, and if we can today, we'll talk about like the code, right, if we can. So also today we'll be most likely explaining the theory for you before we get into the practical side of it. So we'll be talking about transformers, self-attention, maybe training GPT, calling attention, and whatever. So let's see how it goes. So the first things we'll talk about is like what attention is. What is the attention like in high level? What does it mean? What does it mean? So actually, when you hear self-attention, intra-attention, it just means like you have tokens, right? And you want to like in during a pass or during processing, you want to know what's important, right? What's important in understanding the meaning of something, or what's important in the context of this one. Most likely context, right? What's what do I take as priority when trying to understand a word? These are things that maybe our brain does as fast as possible, but they were trying to code it up into the transformer into the deep learning. And so they brought up the idea of self-attention. And if you look at the link I shared with you from J. Alama, yeah, which is down, he also explained it quite well, right? So, he was like at the high level, right? He just look at his word. The animal didn't cross the street before because it was too tired. So if at a point you are trying to process the word eat, right? What should what should take priority in determining what that eat is, or what should you associate the eat with, depending on the sentence. So that's what attention is. So if you look at this diagram, you see that um, the word eats, right, is attended to by the animal most likely because of the heat map. So the higher the heat map, the more attention it is. So this is like a visualization of what's going on. So the word animal, can you, is, sorry, is anyone, can you mute your mic?
Sorry. Thank you. Don't worry, I want to pour it by myself.
Choma, please, can you mute your mic? All right, some mic. Okay, all right. So yeah, the animal is most likely what it should use to determine what that it is. Because it at any other sentence could be anything. But right, so the self-attention makes the model know that okay, at this point in time, I want the what determine the word it are those things at the back of it, right? So that's what like the attention is like in high level, right? And so depending on the context of a word, a particular word can have a different meaning, right? So, like now, this word, I have no interest in politics, and the bank's interest rates rises. So you see that at each point, the word interest will have different meanings. So what determines the meaning of a particular word is most likely the words behind it or in front of it, right? So it's something like context, right? So that's why the whole attention mechanism was brought up to like solve. So at a particular point, the model is attending to or is attending to a particular word at a point. So the whole idea was that there's now something called the attention hedge, right? There's I wish you can see my mouse where I'm clicking. So imagine now you attend to one word at a time, right? And you now have the ability to attend to different words at a time. So something like two heads are better than one. So it just means that the model has the ability to attend to different things at the same time. And also there are now like 12 layers of that. So we see this multi-head attention, right? This ability for the model to attend to different things at a time at different levels, right? So this in overview is what like the attention or like what the attention does and what it's trying to achieve, right? So just like the saying, the cat image here, two heads are better than one. So um, the whole multi-head attention allow the model to like jointly attend to information from different representation sources at different positions. That's most likely some kind of linear algebra um, terminology, but it just makes sense, right? For different parts of a sentence or a different part of a text, there are different things to attend to that determine right what the meaning of this word or what the meaning of this sentence is. So that's what it's just trying to say, right? So now that's all about like the attention. The most important thing about the transformer model or the whole idea of the transformer model, what brought up transformer model was attention itself. On the paper, attention is all you need. That's the 2017 paper. So you can always go back to reference and also read about what was said by the authors of this paper, right? So today we'll most likely focus on GPT. And if you remember from what I said, the GPT is an autoregressive model. And if you read the material, it's also clearly explained here. So in the overview, the transformer is all of this, right? In the overview from the first paper, the transformer is all of this, and it's most likely used in, from here you can see it's most likely used in translation tasks. This suite to Dion, I'm a student. So that's like a transform. This like what the transformer does. You give it some text and it spits out some other text in output, right? So now there is there in under that is that what's under this transformer is some encoders and some decoders, maybe 12 encoders and 12 decoders. And if you that's what makes the entire architecture of a transformer. A whole lot of this and a whole lot of this, all doing some things in between, right? But so okay, to explain more, you see that the encoder from the text and also explained it last week that the encoder is used for understanding input, right? And one example of a particular model is built from encoders that BERT models, bidirectional encoder representation transformer. So these transformers are very, very specialized, right, at understanding text, right, very, very well at understanding text. And so their tasks most likely will be about tasks that require them to understand text, just like sentiment analysis, right? You can you know that when you want to determine the sentiment of a particular text, you need to understand the meaning, semantics, and all of that. So those kind of models are good at that. And now the decoder part of it is used to understand because the decoder, there's a feeding, the encoder output is fed into the input. And also it's it's good at generating words and generating tokens in the future, right? So the output of the encoder is fed into the decoder, and it's also used to understand what the encoder is talking about, and also attend to what like the encoders try to understand from inputs. I don't know if you get like what I mean. So, but for today, actually, we'll be talking about the decoder, which is just the GPT, right? The what happened, or what the makers of GPT, I think that's OpenAI, what they did was to just cut off, I'll also explain it in the future, but they also just cut off the encoder part and just use the decoder like on its own standalone and do some other specialized things in like, on the way. So like the name says autoregressive. So what it does is that it generates tokens from using previous like tokens, right? And the GPT is most likely just a decoder model, right? GPT generative pre-trained transformer. And the tasks are most likely for generative tasks, right? Because what the decoder can do is to generate text. What it's good at is generating text. So it's most likely good in generative tasks like chatbots and all of that that needs you to generate something. Maybe you want to write some papers and stuff like that. So that's what GPT is used for. What is mainly used for. And so this is like a slide of how the GPT-2 worked, right? You give it a start. This most likely start of a sentence token. And when you give it a start of text sentence token, it spits out some tokens, some words like as it goes. So you feed in A, feed in the start of sentence, and it gives you A, it feeds the robot and all of that. So this law is most likely a law in computer science. I've kind of forgotten what it meant, but that's what the autoregressive models are good at, right? So just a look at how the GPTs are, right? How the architectures are. We go from GPT-1, GPT-2, and GPT-3 and see what's going on like under all of that. So the GPT architecture, right, was the first architecture that came out from OpenAI, and it had 12 layers, right? It had also 12 heads. If you remember what I said about heads, right? A particular attention head attends to a particular word, or finds what's important for a particular word. And sometimes, depending on what you're doing, you need to attend to different things at the same time. So that's where they brought about the thing called multiple heads. So at this particular stage, there might be multiple, there were 12 multiple heads. And also this whole layer was like 12 of that. And it had 117 parameters. So 117 million parameters, right? And it was trained on 4.5 gig of text. And I think we all know what parameters are. Those are the weights, because in all of these, they're like weights. You remember from neural networks, you know that there are all these weights that are randomly initialized, and there's a front, there's a back propagation, and all of that. So there's a learning, so the weights will be updated as time goes on. So the same thing as here. So there were a whole lot of those parameters here. It's 117 million of that. And you see that this just for GPT-1, right? And also the data it was used to I was using was just 4.5 gig of text. So it's not really that large compared to the other models that came after it, right? And there was not only GPT-2, right? GPT-2 had 48 layers. Also, it also had like different like model sizes. From the paper, it wasn't stated how many heads it had, but most likely 10 or 12 heads, because it's just like the standard in most cases. Also, it had 1.5 billion parameters, right? We're getting really big here. So we see from here, the 117 million now is 1.5 billion parameters, and it was trained on 40 gigs of text. So we see that what I was saying, that this is going to be one decoder of its own, another decoder. So there are 12 of that stacked on each other. And we see that it was trained on 40 out 48 layers, and there are different sizes of that. So let's go to that. So there is the GPT-2 small, GPT-2 medium, GPT-2 large, GPT-2 extra large. And depending on number of layers, it also depends on also determines the size of the model, right? As you have more layers, you have more model weight. As you have more model weight, the size increases. Right? Well, all these weights have to be stored, all of that in memory and all of that. doing the updating. And so that's why the sizes also increase as the layers increase. Also, you see the model dimensionality is also like the embedding layers, right? They are the embedding layers that are fed into the model, right? So that also was increased as the model size increased. So we see here from 12 to 24 to 36 and to 48 layers. All of that's for GPT-2 extra large. And you also see that in BERT models too. If you remember, also T5 models, they are just depending on the use case or whole lot of things that because of all of these models have sizes, and you go with the sizes, you need to map more like resources, storage resources, GPU resources, just to load this model. So depending on your use case, you can always choose which one you want. So now this GPT-3, right? We see that they went farther, they went like higher than they expected. So it was trained, the highest was trained in 96 with 96 layers actually. It has 175 billion parameters, and it was pre-trained on 570 gig of text. So I said pre-trained, right? Because I maybe if you've done something, say you know what pre-training is. Like I said, it was pre-training is just like you want to let these models have like knowledge of language and all that. So you have some text, maybe Wikipedia, some of times the Reddit, there are some books, literature books, all of that, and they have this large text. So it learns to with some specific tasks to predict or to generate some text and all of that. There are a whole lot of pre-training tasks out there just to help the complexity. So yeah, so each layer had 96 heads. So we're talking about a very, very huge model here. And you can see the different sizes also. We can see the layers. We can see also with the layers, they were heads. So they outdid themselves OpenAI. And you can see for something like 175 billion parameters. I've forgotten like there's a scale, depending on the parameters, how much gig you need. You can also do that research, right? All these parameters determine how much gig you need to train it, right? So how many gig of GPU memory or how many GPUs and also the scale of GPUs you use to train. So when you want to train your own GPT-3 model, you know what's at stake for you or whatever model you want to train. So like I've been saying also, the GPT style model doesn't have the encoders, it doesn't have the embeddings, it doesn't have the the output of the encoders into the decoder. It just has these layers, right? The multi-head max attention. We also explain what that is, the input, shifted rights, and all of that, and some also training tasks also. So we are going to like go maybe more in depth into the attention and all of that, or give some examples what it is. So now the training style of GPT-3 architecture is like this. You have some sequence, you have the stats of sentence sequence, and there are all these passes depending on the length of the sentence. And what you want to do is to like predict what the next word will be. So the whole transformer decoder has all of these. There's this max self-attention, which we'll explain. There's the feed-forward neural network. We all know what the feed-forward neural network is, right? It's just like a normal linear layers where you have matrix, multiplications and weights and all of that. So inside the decoder block, there's these two things inside there. So let's move on. So the difference between when you have because you just have the decoder network here, right? So you want there's a different way of training something like that, and it's called the max self-attention. Remember when I said it here, the max self-attention. So what this means is that because you want to generate a new token or a new word, depending on the word you have a loss function, all of that, right? Depending on the words, that's how we learn. So to do that, you have to mask the output, right? So what does that mean? You give it until the right thing, the pass you are in, or the time step you are in, whatever language you want to give it. So an example of using just this self-attention is something like translation, like machine translation. That's why the whole T5 model was used in translation, right? Because in translation, you have all of the text already at like in place, and you want to know what to attend to translate to a particular language of choice. So, but when in the GPT-3 style, there's this mask self-attention. So some words are going to master depending on the time stamp you are in. Right? So that's how it is. So you input the start of sequence and it just tells the model that it's time for you to start um reading like predicting token. Like so you put in the start of sequence and it just gives you D, and it makes sense that the first word in a sentence should be D or A or whatever that, but that's just how it is. And after putting you feed the inputs of the output back into it and it gives you thing and all of that, and it all goes on like that. So checking the time, the slides are very many. So we might have to break and continue this week on Friday. Sorry for the breaking, but it's a whole lot of materials. Like you expected that. So yeah, so how is this happening? Like um a word, yeah, there's a word, right? And how does the model understand all of this, right? So um, the model looks up the embedding of the input word, right? So you have a word, and it's most likely going to be converted to numbers, and that those numbers are now going to use to look up an embedding matrix, right? And that embedding matrix is actually created during training. We'll also explain what that is, right? So, like you most likely have a vocabulary size, maybe this is 50,000 or less. And it's also the embedding size. There are different sizes. There's small, 768, there's medium, there's large, and so depending on how you say how much resources you have, how much accuracy you're looking to get, you can also like increase your embedding sizes too. Right. So let's continue. There's also, if you remember from here, let me go that back. There's also something called the positional encoding too, right? Um, if you are familiar with the previous ways we did natural language processing, like with the RNNs, LSTMs, GRUs, right? There's something about them is that they're recurrent. I will also explain this in the future, but what those did is that they kept the sequence of the words as you're training. But normally in the attention, there's no way to do that, right? So they had to introduce something called the positional encoding. And that also is also part of the layers before heading to the attention layer. So it helps in keeping the order of words, right? Because like I'm recapping again. It was recurrent. So one goes first, then next goes. That's why it was also not scalable. But in attention, you can scale, but you also want to keep the other word because you don't want a word to also seem to come before another because that scatters the whole sentence or the whole understanding of the sentence. So that's also there. And so so what happens is that there's a word is looked up in an embedding, and in that embedding it's converted to embedding vector or matrix, and it's fed into the positional embeddings, and that's also now fed into the decoder. So that's how it's all done. It's linear soft and the softmax. I think we should have an idea what the linear softmax is. Right? It produces a probability distribution and all of that. So that is understandable. So let's go into the embeddings, like what the embeddings are, all of what it means. Right? So if there are any questions, you can always drop them in the chat box. So like in the material, you see that you need a way to represent text, right, in numbers, right? Because you don't expect your computer to understand text, right? So we had to, or they had to, I was not the researcher, but they had to come up with a way to represent text in numbers and also keep like the semantic meaning and also all of what it meant in numbers, right? So they brought up what's called the embedding. It's almost like a space. If you've done linear algebra and all of that, or just geometry, we know that in a vector, there's a three-dimensional space, there's two-dimensional, there's not n-dimensional. So we're talking about the more dimensions, the more like space or more meaning you can keep, but let's just leave that for the future. But yeah, so we want to create vectors that have like representational meaning in their spaces, something like that. So That's just like a small, like a simple way of talking about it. So just for an example, right? You have where would you put the word apple? There's this like baseball, basketball, football. There's the houses. I think there's a house, so a church, and what these are cars, bus, bicycle, and this is the ferry, banana, whatever this is. So what embeddings help us do is that they have this kind of way of keeping the meanings or the close meanings or context of words. So just for an example, where would apple be? Apple most likely be near where the fruits are. That's what the embeddings help us to. Also, something like this, also cow. Even in like cow, this is a cow, a puppy, a dog, and where would the cow most likely be? Most likely be in sea, where the cow feeds. Even though these are all animals, in that space too, there's just a way, and it's mathematics and some visualization that um the it finds a way to keep similar words together and also similar meanings and context together. So that's the power of the embedding models, also the embeddings. So there were two types of embeddings. There's the one with context and there's one without context. I think we know what context in, right? Like when n-dimensional space are what's related to one another. So depend where a word is, right? It it's also like where in a sentence the word is also determining the context of it. Like so the surrounding words of a word or a sentence determine the context. So there were two ways of doing embedding. There's the context and the no context. And the no context are the old NLP, early days of NLP ways, right? So what embeddings do is that, in a particular subspace, there it might mean something, and but in another space it means something else, right? So it kind of captures context. A word's context. Like if you remember when we started the word interest. So interest in some places could mean feeling. Interest in some places could mean money. So the embedding will find a way to um, capture those meanings in its different subspaces. So that's why it has this kind of long 4,096 let me say dimension, something like that. So in all of that, it finds a way, or the model learns a way of capturing all those contexts in these numbers and in dimension. So and as a side, if you remember linear algebra, um there's something called the matrix rank, and like it determines the number of, like if you want to actually visualize it, right? There's this thing, there's PCA, but there's something about the matrix rank. It knows how many number of linear independent columns in the weight of parameter matrix. So when you ever want to visualize, so it is a way that matrix rank is calculated, and you kind of find a way of visualizing this embedded and see that some of these close these words have close meanings, and it's found a way to represent them in subspaces. So this is kind of um, side story as a kind of side. So in the past, when we wanted to do embeddings, we did something called bag of words. We did something called TF-IDF that vectorized or normalizes the bag of words and counts of vectors. Because the bag of words is just a count, and TF-IDF finds a way to normalize it and keeps like the word number of words and his appearances in the document. So that was, but there was no way for this to capture the context in a sentence, right? So he brought up something called word to vec, continuous bag of words, and skipgrams. These are all techniques that are kind of outdated right now since the introduction of the time flies, since the introduction of the neural network and all of that. So for the embeddings, the step was to use something called the neural network. And if okay, just a recap, if you remember what to vec, right? What to vec was a very, very fascinating thing. He found a way of keeping the context, like find a way of like using the vectors to do some mapping, right? So this was like some way back when this was the trending thing, where you can just do king. So you have the vector king, you subtract the vector man, add the vector woman, and you approximately get a vector queen. So if you get a vector, if you set the nearest, maybe an Euclidean distance or whatever distance metric you're using, you most likely find the nearest vector to it was a queen. So it was fascinating at then, and that was how word embeddings were created back then. So, but now neural networks and the attention and transformers. So what's actually done is use the hidden layer, right? So if you remember in neural networks, there's the input layer, there's the hidden layer, and there's the output layer. So what that does is that you see that it expands words and like find a way to capture all of the context in the hidden layer or the embedding layer, if you want to call it that. So you know that the hidden layer is just weights, right? They are just weights. So it's a way of learning these weights that captures the context of words, right? Using a neural network attached to attention or LSTM. I think LSTM, LSTM RNNs, and also the transformer models. So um, what's this? So yeah, this is going to talk about the initialization. Actually, when you just start, before you actually start training, just like in a normal neural network, all of the weights are initialized random. I think this is uniform distribution, that be Gaussian distribution between 0 and 1. So at first, this is how it is created at first, before the back propagation is, sorry, not backdrop, back propagation is done to update those weights, right? So it learns as it goes. So that is how the initial start, that's how it starts, right? The outputs are maxed, like so they are just like zeroed out, something like that. And there's now the neural network for computing the embedding, the text embeddings. So before you get into the attention, there are most likely one, two, three, four, five um embedding. There are five neural networks that are used to calculate the text and position embeddings in a transformer model. So what is learned are those hidden layers. Those hidden layers are what is learned and what to be. That's how you get your embeddings. And you can just use the embeddings for maybe some of your tasks that you might want to do. It just requires maybe similarity or semantic comparisons and all of that. So that was the first part of the attention, sorry, the transformer model. Right? So there's now something called the positional encoding. Right? So since the transformer model, if you can read this, some transformer model has no recurrence and convolution, we have to find a way to inject the position of the tokens in the sequence. And to do that, they came up with this formula. This should be come out. If you finally know why they came up with this formula, please drop it in the chat or in the Slack channel, right? So we can always learn. But it's something about sines and cosines and them keep the ability to keep like sequences, just sinusoidal waveforms, something like that. So it has a way of keeping progression. I think that's on paper. So it was also, there were other ways of keeping positional encoding. Sorry, the positions of tokens, right? There were other ways at then, but the standard way was, or the way that the people in the paper brought up was the positional encoding using this sine and cosine. They found that it was good enough. It was still performing well enough, right? Using the positional encoding. So this is thus them releasing, with every paper they release why their paper is good, right? They use they're comparing their own method with other methods. So they compared their method with before the positional encodings, you have to learn positional embeddings, right? So you're now learning more things and it's taking more time. So what this is saying is that using just positional encodings give almost the same scores with learning this positional encoding. So that's why everybody now sticks with the positional encoding. I hope like that explains this. So setting up for the positional encoding, what goes on is that words are chopped off. Actually, this might not just be financial, depending. The financial might be split up depending on the vocabulary. And sometimes tokenization is also learned. Like you learn how to tokenize words. There are all these advanced tokenizations, and you might cover it in the coding session actually. So the sentence is split up into tokens, and those tokens are keep split into numbers, and those numbers are used to get the lookup, the embeddings, and we now add the positional encoding also on top of that. So before it's giving into the attention layer. So it's something like this: write a story. You just have a word, a sentence, write a story, split up. right? A story. Then each is given a number. You used to look up an embedding matrix and you get the embeddings. And so these embeddings and the positional encodings are now fed into the transformer model or the attention mechanism, right? So that's how. So this for just a simple example. I'm just going to use a simple example to explain further. Once upon a time, right? So this is me explaining again. Once upon a time, it's fed into a tokenizer and it spits out some values, right? Depending on what that tokenizer was trained on, right? What the vocabulary is. I think the vocabulary matrix or whatever, I've forgotten the term it's called. So it's going to create some numbers, and those numbers, right, are now used in an embedding layer, right, to come up with an embedding vector. So going to, yeah, to get the embedding vectors, because the embedding layer is most likely a matrix. It's just doing a lookup or just doing a matrix multiplication, right? So you get those vectors depending on the embedding size. Sorry, the embedding size you use 768, 1000, blah blah. That's how it's done. So it's now the positional encoding is now done by taking the current position. So once is the first, so position is 0, right? I'm sorry, this is supposed to be 700 and this is okay, 700 and yes, 67, right? That's correct. So the 0, this is going to be 0, 1, 2. So 0 to 767, 768. Hope that makes sense. So you carry 0, put it into the formula and get a number. So you get like 768 of them. So it matches the embedding vectors. So you do that for ones, you do that for upon, you put 1 into the formula, you get 0.84, all 768 of them, you go on. And so you have something like this. This is just a small visualization, but as you go on, we see that this is 1010. Sorry, this is 0101 and 0.84, 0.57, all of that. And it goes on to it. So that was just for what was the embedding dimension? 10 dimensions, 4 tokens, 1, 2, 3, 4. But if you increase it to 512 dimensions and 4 tokens, we don't still get like a picture. But when you increase it to 100 tokens and 512 dimension, we see this kind of sinusoidal representation. So this is what the whole positional encoding is helping us do. It's helping us keep like the positions, right? Keeping their positions as we attend to all of them simultaneously, because that's why the attention mechanism was brought up in the first place, for easy scaling. So you don't need to wait for ones to go in, then wait for upon to go in, then wait for, yeah, that's just it. So now what this means is that we have the positional, we have the embeddings, then we have the positional. So the two embeddings are now added up to form the embedding that is fed into the attention mechanism. Why is it added up? Because if you just concatenate them, you're going to create another vector space on its own, right? You're creating a vector space and you don't even know whether it matches with the other one because remember, the embeddings are used to keep the context, the semantic meaning, and all of that. So adding another vector, concatenating another one would like create another space and might scatter the whole relationship that might be developed from the word embedding. So you just concatenate them. Sorry, add them. You just add them. And when you add them, you're still retaining the relationship, because even if you add you're adding one to each of them. So even if they shift, all of them are shifting together, if you get the picture of what I'm saying. So that's why these two steps are done before you go into the attention mechanism. I'm not seeing any question. I'm guessing that everyone is understanding now, right? So let's continue. So let's go into the attention. So the attention has some in-depth tasks, like things happening inside of it. Right? So we see there's the imaging multiplication, there's the scaling, there's the masking, there's softmax, there's the imaging multiplication, and that's what is done in the scale dot product attention, just this layer, and all of this is what is inside here. Right? So you see that there's a whole lot of mathematics, sorry, matrix multiplications, matrices, calculations that are done just in one layer of the attention mechanism, right? So you can now reason why there are a whole lot of that. You can see that there are different heads, right? There are different heads of that, and also different layers of that. So you can see how far, how large the computations are going to be in this attention, in this transformer model. So we're going into something now. We're going into what this QKV means, query key values. And for that, we're going to use something we're going to study in the future, RAGs, retrieval augmented generation. So what does that mean? Retrieval, you're trying to retrieve something in your document. Augmented, you're adding references to your prompt. This will all be explained in the future, actually. But what it just means is that you have a query, you want to search for a particular thing in your PDF. Like you want to maybe have a biology textbook and you want to say, where is the reproductive system, or what's the reproductive system? You want to ask GPT something like that, right? And GPT might not be good enough, right? Depending on how specific the case is, might not have been trained with that biology textbook. So you want to read on your own biology textbook. So you have a query, where is the reproductive system located, stuff like that. So you have that query, and what happens is that query is fed into an embedding model. Remember, there's embedding model, right? So it's convert that to numbers, and that query is also put into your prompt and is now used to search for similar documents which are going to be retrieved and used to ask GPT the questions. And that was just like a fast way of explaining it. Because of time, for 42, we can always continue next week actually. So I'll just continue. I'll explain this later. Okay, so query key value. So the query key values are just like there was something like the researchers brought up about so you want to have a query. Your key means the document in your vector database and value all the documents called by similarity, right? So what all of that means is that you're just calculating similarity like a dot product, right? The dot product is just like calculating similarity. So what's happening is that you have a query, right? And it's going to be converted to a vector. And that vector is now going to be used to search in the database. What are the similar things to this query? And it's now going to return that to you, right? So from here, you see the Q is query, the question asked. K, the key is that all the documents in vector database, and value are the documents that are returned out based on their similarity. I know this might, I don't know if it helped your explanation in explaining, but if you can also check out this, material by J. Alama, it will most likely explain it better for you, but I'm still going to continue. But depending on time, we might not be able to finish it today, and I'll continue on Friday. Sorry about that. So let's continue. Slide is loading. Okay. So what's just happening is that it's calculating similarity. And we know from, if you have background in mathematics, linear algebra, cosine similarity, if you have vectors and the closer they are to angle, the closer they are, the higher the value. Because cos 0 is 1, cos 90 is 0, if you remember trigonometry. So the closer the two vectors are together, the more their value. So the farther they are apart, the lesser their value. So that's something about cosine similarity. That's how the whole cosine similarity and similarity is calculated. So what does this mean? What does this actually mean? So what it means is that in calculating the attention, we are looking at what is similar to this particular word in this sentence. So what does it mean? An attention function can be described as mapping a query and a set of key value pairs to an output, where query keys, values, and outputs are all vectors. The output is computed as a weighted sum of values, where the weight assigned to each value is computed by a compatibility function, which is the dot product or whatever of the query with the corresponding key. All right, sorry about that. So what does that mean actually? So in the whole attention mechanism, there are a few calculations that come into play, right? There is the query and the key multiplication. There is the scaling, that is this here, the division by the square root of the dimension of the keys or the word embedding. There's the softmax, and we all know what the softmax is. Just going to output probabilities, numbers between 0 and 1, and they sum up to 1, right? They must sum up to 1. And there's now another matrix multiplication between that score, those numbers between 0 and 1 with the value. So we see that it's going to be like a weighting, right? If the value is 0, that means there's nothing, they are not similar, there's nothing to attend to, something like that. But if the value is 1, that means attend to this thing as much as possible. So that's just like the overview or fast overview of what is going on. Yeah, but I'll still explain it as we go. So like I've been saying, the matrix multiplication is somehow like the dot product. It's just that they are if you've done linear algebra or what linear algebra, that's where it's be explained. We know that if you do dot product of two vectors, you get a single number, right? But if you now put the vectors, like add them up to a matrix and another matrix, you are most likely doing a dot product, but they are doing it in another scale. If you get the picture of what I'm saying, doing matrix multiplication is actually doing dot products. So that's what it is. So when you're doing dot products, you're calculating similarities across vectors, right? So this is actually done by a linear linear. So if you hear a linear layer, you're most likely talking about weights and matrix and multiplications too. So there's also the scaling, because after you've done a multiplication, you are most likely sure of getting values that are high and low depending. And so just like in linear regression, high values affect the back propagation and all of that. The same thing also in transformer models. Is that a question? See. Okay, this is lab that will be answered in Slack. I'm sorry. So the is going to scale that so that the numbers don't get too huge, or they're not like outmatching themselves, like comparing a value from 0 to something like 1 million. That would be very, very wrong. I think this should have been taught like in linear regression and all of that. If you have linear regression like expertise, you should have seen why we did something like min-max normalization, standardization, all of that. So that's why we did that before before we did the soft marks, right? So we do the soft marks to ensure a list of values that sum up to 1 and measure gradients in a landscape. That's research related. There's also the masking. I think I skipped that, but like I said, the masking prevents information like left-out information flow, right? So it prevents the model from knowing too much, because if the model already knows, it's not actually going to learn, right? It's not going to learn. So that's why they mask it out and tell the model to predict something so we can calculate the loss function and do some actual learning. So that's all of that. And we now have another matrix multiplication. So remember, right now, after the softmax, we have scores, right? You have like a list of scores. And so we're now multiplying that with a vector or a matrix, whatever that is. So what that is, maps that query key I've attended. We have mapped what the query key I've attended to back to the embedded encoded information. So this is what you're supposed to attend to. Now we're telling you what to attend to, right? That's what it just means. So we see that these researchers found a way to do reasoning with mathematics. So that's all of why the field of NLP has been growing so much. Right? So I think I have like 5 minutes more because we have in another session in a few minutes. Okay, so like I said, so the attention function, I think I've explained it, so let me not repeat myself. So also, now if you've looked at this material, please, I implore you to look at this material. There's no better way of explaining it. There's no better way to explain the attention mechanism than how J. Alama explained it in his material. He also has a YouTube video if you are one that likes videos rather than reading long bunch of texts. Right. So wow, people are already coming in for the other session that we have. Okay. I think I see a question. Can you share the material? Okay, definitely. We'll share the materials. All right. So I think I also shared the link in the previous material, but I don't know if that was shared with you. But let me just continue. So we have this just it in simpler form. We have the word thinking, we get the embedding of that word, and then we get the query key values from the embedding. That way we explain why that is done in future. So the query and the key, we have a dot product, we get a value. We divide it by the dimensionality. Right now we just 8, we get 14. We do softmax, we get 0.8. You know, softmax has to do with a group of values. So these two add up to 1, right? And now that softmax value is now used to multiply, that softmax score is used to multiply the values. And we now get this, the sum. So we see that 0.88, this one is most likely going to be attended to more than the other word machine. So we see that 0.12 times that will most likely 0.08 out. So at this point in time, thinking is most likely attended to more, or there's more attention to it than the word machine at this particular pass. I see 2 questions. I learned, oh, okay. All right. Shared on Slack. It will be shared on Slack, definitely. Okay, let's go on. So what does this mean? Query key value. So query is the new token, right? In a particular, what is the um, model I think like working on now? The current input to the transformer model is Q. So key and value are all every token in a sequence, right? In the sentence or whatever. So Q is the query. Like I said, what you're searching for, right? What does this query? What are the words that are important to it right now? And these are there are also the keys and the values. So what happens is that at the first pass, after the start of start of sequence token, so once is the key is a query, once and this is the key once and this, and the output is upon. So that's how it goes. Upon is a query, once upon, and all of that. The output is a. So that's how it goes um in the attention mechanism. So, but one thing is that using just vectors is not, oh, I think I lost some of my slides. Oh, yeah, using vectors is not what do you call it? It's not best practice, right? So what is best is using the matrices to do these calculations. But I think some of my slides are not here right now. So what I'm going to do is that I think we're going to stop for today. And in the in if you have any questions on why I work on why my slides are not showing now before otherwise not showing before if there are any questions, please. So by next week we're going to, I know that I've given a lot of like I've talked about a lot of things. Well, I've gone to 78 slides right now. And I know if there are any questions, please you can drop them up on Slack, and you can also drop them up here right now. But I think this is the end for today. Next week, sorry, not next week, Friday, we're going to the code and also completing this whole attention thing. But I'm sure we're already done with it. We're already done with everything. Just a few slides. Just need to figure out why some of them are not showing. Right. So if there are any questions, please and please, you need to do some research. You need to learn if you want to get through this stage, right? There are there are some like things you need to know, right? There's some concepts you need to understand, and I've been sharing some of those resources with you. So like whoever that said, you can always try to study alone, or there are also groups that you can study with. You can also meet up and study. But this is quite large material. It is not really important for the next stage actually, because we don't want to get you guys bored with theory, right? Too much. We want to get you guys to building um actual stuff with this. So this is not really that important for you to know to get on with the other stages, stage B, stage C, stage D, right? But if you want to stand out and all that, it's required that you have some knowledge of what all of this does. So um thank you so much. I see there are no questions. They're just questions as you share the slide. I will share the slide with the Amoye admin, and he or she will get it to you in Slack channel. Thank you.